Everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we will have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Philip Thomas. Dr. Phil Thomas is an assistant professor at the University of Massachusetts at Amherst. He received his PhD from UMass in 2015 under the supervision of Andy Bartow, after which he worked as a postdoctoral research fellow at CMU for 2 years under the supervision of Emma Brunskill before returning to the University of Massachusetts. His research focuses on creating machine learning algorithms, particularly reinforcement learning algorithms, which provide high probability guarantees of safety and fairness. He emphasizes that these algorithms are often applied by people who are experts in their own fields, but who may not be experts in machine learning and statistics. And so the algorithms must be easy to apply responsibly. Notable accomplishments include publication of a paper on this topic in Science entitled Preventing Undesirable Behavior of Intelligent Machines, and testifying on this topic to the US House of Representatives Task Force on Artificial Intelligence at the hearing titled Equitable Algorithms, Examining Ways to Reduce AI Bias in Financial Services. Today, Dr. Thomas will talk about safe and fair machine learning, a Seldonian approach. Welcome, Phil, and over to you.
Thank you for the nice introduction. Hopefully everyone can see my slide. Let me know if for some reason that's not the case. And hopefully you're seeing just the main slide. So thank you for the very nice introduction. Again, I'm very happy to be here and to have the chance to talk to all of you about this work. So in this presentation, I'm mainly going to focus initially on this paper that David just mentioned, Preventing Undesirable Behavior of Intelligent Machines, which was work with these many fantastic co-authors. So I'll start with the claim that AI systems are already impacting our lives, from medical decision support to autonomous vehicles to software that looks at your resume or looks at resumes submitted for a job posting and determines which one should be looked at by a human, to software that influences criminal sentencing. But with the growing impact and influence of machine learning applications like these, there comes an increased potential for harm when these systems misbehave. So examples of this include IBM Watson giving unsafe recommendations for treating cancer, Amazon having tools that show different forms of bias, and there are many different pieces of software that have been shown to exhibit different biases and unfair behavior, to autonomous vehicles that have already caused fatalities. For a while, there was a list of fatalities due to self-driving cars on Wikipedia, though interestingly, that list is no longer on Wikipedia. And one example I want to highlight, because I'll talk about it a bit more, and I see there's something in chat briefly. I see just a welcome message. So one thing that I want to highlight is this article, Machine Bias by ProPublica, as it's a good motivating example. So this article was published by ProPublica studying software produced by a company called Northpoint. And the software that Northpoint produced takes as input a description of a person and predicts whether they will commit a violent crime in the future. And this software was actually used in 11 states in the US during criminal sentencing. So a judge would see the prediction of this software, and that prediction would help inform them in their decision of how long that person should spend in jail. ProPublica studied the predictions that the system made and the actual resulting outcomes and found that there was some bias, specifically if we only consider the people who did not go on to reoffend, the people who did not commit a violent crime in the future. The system was twice as likely to say that they were likely to commit a violent crime if they were Black. So misbehaving ML systems have already caused harm, from in some cases killing people to reinforcing these existing social inequalities. Okay, but there's another form of harm beyond those that I've already talked about, and that's a missed opportunity cost. That's that there are many proposed applications of machine learning that aren't coming to fruition. And I think this is especially true in the context of reinforcement learning, which is the area that I study most. So let's talk about a few proposed use cases for reinforcement learning. One is sepsis treatment in the ER. This was a Nature Medicine paper proposing the use of reinforcement learning to treat sepsis. And even a small improvement here would be a massive benefit to society. 1 in 5 deaths worldwide are due to sepsis. Reinforcement learning has been proposed for type 1 diabetes treatment, initially by I believe, folks from the University of Alberta. And then we talked about it as a potential application in our paper. Oh, sorry, this one isn't type 1 diabetes. This one is epilepsy. It was proposed by, this was, I believe, folks from McGill who proposed using reinforcement learning for epilepsy treatment. And as I mentioned, type 1 diabetes. Also, back during my master's, we studied putting probes into a paralyzed person's arm, because often when someone's paralyzed, everything's intact below, for example, a break in the spinal cord. And so you can stimulate muscles directly in order to move a person's arm and then try to give them back control. It's another proposed application of reinforcement learning, all the way back to one of the oldest, which is just deciding which floor an elevator should go to next in order to minimize total wait times, which is one of the earliest proposed uses of reinforcement learning. So though these applications have all been proposed, not one of these has actually come to fruition. There's a common misconception that the elevator example actually happened. I talked to Andy Bardo about this, who's the one who described it in their book, his book with Rich Sutton. And he said they went to Otis, the elevator manufacturer, and they tried to convince them to use reinforcement learning, and Otis said they couldn't get it working. So it's not actually in use, as far as we know, for elevator scheduling. So none of these applications have actually happened. So if RL hasn't been successfully applied to any of these proposed applications, what are the successes of RL that you've probably heard of? So you've probably heard about reinforcement learning recently because it's been in the news a fair amount and it's quite popular. So what are the successes that have made it popular? The successes are largely video games. So it was used initially for playing Atari games. It's been used for playing Doom. It was used to play, in this case, not video games, but board games, to play Go and chess, different multiplayer games, StarCraft 2, Dota 2, Minecraft. The list goes on and on and on. You could fill dozens of slides with the examples of reinforcement learning succeeding at playing video games. So why is it that RL is effective for video games and other games, but not the high-risk, high-impact real-world applications that it's been proposed for? And I think the issue is one of safety. Reinforcement learning algorithms just simply aren't safe enough to be applied to these real-world applications. So often when you apply RL, there are many different hyperparameters you have to tune. Once those are tuned properly, it might work well for that problem, but there's no guarantee that even with the best parameters, it will work well. And this is completely okay for video games, right? No one cares if you lose billions of games of Mario on Google Compute somewhere while you optimize your step size, your network architecture, exploration rate. That's okay. It's not causing significant harm beyond perhaps a waste of energy. But that's not true for the real life applications. We cannot deploy our system and then tell someone, sorry, we gave you a bad medical treatment. Hopefully we'll get our step sizes tuned in the future to give proper treatment to someone else, right? So this risk, this concern about safety, I think, is what's really holding RL back from being applied to these high impact real world use cases. And so also if you're sitting there thinking you'd like to apply reinforcement learning to some problem and the whole world is doing this and you're the one who's missing out and unable to do it, that's not really true. There are almost zero actual deployed uses of reinforcement learning that are making money today other than games. The one that I know of is it's being used for serving up advertisements, and there was one other that's not coming to mind. But most of the others are just proposed uses of reinforcement learning. So I hope I've convinced you that there is a strong need for safe machine learning algorithms. And this is because ML systems already have caused harm. And by creating safe ML algorithms, we can prevent that harm in the future. And second is that missed opportunity cost, that there are many applications that would be reasonable, but the responsible use of machine learning for that application is precluded by very reasonable concerns about safety. Okay, so given this growing importance of safety as machine learning algorithms are used more in the real world, and the harm that misbehaving AI has already caused and the applications that are prevented by concerns about safety, my goal is to make it easier for the person that's applying a machine learning algorithm to control the behavior of the resulting system, to ensure that the system is safe or fair. And there are at least two different routes that we can take towards this goal. You could break this in many different ways. I'll just split it into two potential routes. One is ensuring that machine learning systems are obedient. And by obedient, I mean we make it easy for someone to tell the machine learning system what they want it to do, and the machine learning system will then guarantee that it will do what the person asked of it. The other thing that we could try to study is preventing unanticipated behavior. So how do we create a machine learning system that even if I don't think to tell it, don't produce this undesirable outcome, it can recognize that there's some bad outcome that might occur. And often this unanticipated behavior kind of relates to imbuing agents and machine learning algorithms with their own notion of morality or ethics, or trying to get them to copy our goals and infer what it is we want. So we're not going to study in this talk or really talk about unanticipated behavior or embedding agents with their own sense of right or wrong or morality. We're going to focus on the left side, which is how can we create machine learning algorithms that make it easy for a person to say what we want it to do, and that then guarantee they will produce that behavior. Okay, so to really dive into this, the first thing I want to do is talk about the current way that machine learning algorithms are applied and point out where I think the flaw is that makes it hard to ensure those systems are safe. So this is how I view it today. A researcher designs a machine learning algorithm, which they provide to the community, either as pseudocode or perhaps a software library. The user then applies this to a specific problem, to a specific application, by providing that algorithm with training data, which the algorithm uses to train a model that is used to make decisions or predictions in the future. So this could be data about applicants to a job and how well they actually did in the job. And our prediction could then be for a new applicant, how well would they do if we hired this person? Okay, so let's see what I want to say next. Right, what I want to say next is that the challenge within this setup is that the burden of ensuring that the algorithm is well behaved for the application at hand falls to the user. And I think this is really clear if we look back at the North Point example, the example of the software that was predicting if someone would commit a violent crime in the future. I know when I first heard about this example, and I suspect when most people hear about this example, you think, wow, North Point, the company that created the software, they really messed up and created an unfair system. What did they do wrong in applying machine learning to this problem? Right? We don't say, what did we, the machine learning community, do wrong that made it hard for North Point to do the right thing, to create a system that was fair? And North Point responded to this article saying they did consider fairness and they did try to make the model that they trained fair. And then there's an argument back and forth about that response, which we won't go into. But the point is they claim to have thought about fairness before, and they just failed to enforce a fairness guarantee. So I would argue that this really points out that we are blaming North Point for this, because it's their job to ensure that they're applying machine learning safely to that application. And I think this is a huge problem. As David mentioned in the introduction, one thing that I'm interested in is this question of who's applying machine learning in the future. More and more, it's people who may not be experts in machine learning and statistics, though they may be experts in their field of expertise. So for example, geologists use machine learning to take features describing a slope, the side of a hill, and predict how far a landslide would go if there was a landslide on that hill. And those predictions can be used to inform how far a house should be built from that slope. So this would be an example of someone who's a geologist who may be an expert in their field, but not an expert in machine learning or statistics, but where failure of the machine learning system could be very costly or dangerous. So we need to make machine learning systems that make it easier for this user of the algorithm to enforce safety or fairness constraints. So how do we do that? The goal is to shift this burden from the user of the algorithm to the designer of the algorithm, so that ensuring the system is safe becomes the job of the machine learning researcher creating the algorithm, not the person applying the algorithm to a specific problem. Okay, so here's how I want to change this diagram. Right, so there's a lot to say in this. So the main thing, I don't think I have animations here. Right, I don't. So in this setup, the researcher is now providing two things, not just the algorithm, but also what I call an interface. So when the user applies this algorithm and interface to their problem, instead of just providing data, they're also going to use the interface to provide a definition of what undesirable behavior means for that application. What does safety mean for this application? What does fairness mean for this application? And the researcher doesn't necessarily know ahead of time what this algorithm will be used for. So they can't ahead of time say, this is exactly what safety or fairness should mean for your use case. Instead, the user is saying, for my problem, this is the definition that I want to use. And I think this is also an important component, because if we, the researcher, say, this is, I think fairness is a great example of this. This is what fairness means. And then a user has a different definition of fairness, they're not going to use our system, right? They're going to try to do something else. So for users to use our systems, we need to be able to accommodate the notion of safety or fairness that they have for their application at hand. So the user is going to use this interface to define undesirable behavior. The Seldonian algorithm, so you can just think of this as an algorithm for now. I'll define Seldonian shortly. This algorithm takes as input both the training data, just like before, as well as this definition of undesirable behavior coming from the interface. And as before, it then trains a model that makes decisions or predictions that could impact people in the future. But the difference is this model should then avoid that undesirable behavior. And to formalize this just a little bit more, the exact result we want is that for any definition of undesirable behavior that the user can provide through the interface, the algorithm must ensure that the probability it produces that undesirable behavior is at most delta. So this is going to be a high confidence safety guarantee, saying with high probability, with probability at least 1 minus delta, we will not produce the undesirable behavior that you defined. And the user is free to define undesirable behavior. And another thing, where does that delta come from? The user gets to provide delta. The user provides the confidence level that they need for the application. For some, this could be very high. For others, where safety or fairness really isn't as critical, this could be a lower probability. Okay, so I mentioned earlier this interface, and I think this is very abstract and hard to envision. I'm not tied down to there's one perfect interface. One of the research directions is coming up with new interfaces that are useful for other applications, but we can give some examples of what these might look like, and some are better than others. So in the first interface, you could imagine that a person is faced with this console and they are asked, how many definitions of undesirable behavior would you like to enter? In this case, 1. And then enter the definition of undesirable behavior that you'd like to use. And in this case, the application at hand it's a data set that includes students' application, some information from a student's application to university, along with their GPA at university during the first 3 semesters. And what we'd like to do is predict from their application materials what their GPAs would be, perhaps as an initial filter for who would be admitted to university. But we'd like to do so in a way that is fair with respect to gender. So someone might say fairness in my case means that the absolute value of the mean squared error for males minus the mean squared error for females. And this might be a little weird. What is the -1? Well, the way that this expression is parsed is undesirable behavior means that the thing you type is greater than 0. So in this case, you can move the -1 over to the other side, and you see that this says the absolute value of the difference in mean squared errors being greater than 1 means that this was undesirable behavior. So this says our accuracy for men and women should be similar. And then you specify the probability that we want this to hold with, which could be 0.95. But this interface helps, but it still requires someone to have some familiarity with machine learning and data science. Another example would be what we did in the science paper for type 1 diabetes treatment. Here, let me describe the problem briefly. Someone suffering from type 1 diabetes, actually, first, when you eat a meal, it increases your blood sugar, your blood glucose levels, and your body then releases insulin, which promotes the absorption of that sugar from your blood into different cells in your body. A person with type 1 diabetes, their body doesn't release enough insulin, and so the sugar isn't absorbed enough, and they end up with high blood sugar levels. And when the sugar levels are too high, this is called hyperglycemia. Glycemia for sugar, hyper for too high. So the way that this can be treated is by injecting additional insulin into the person's blood. And there are different forms of insulin. We'll focus on bolus insulin, which is insulin that's injected just before a meal. So right before a person eats a meal, they inject this additional insulin to promote the absorption of the sugar into the different cells in their body and keep their blood sugar levels down. There's a problem. If the blood sugar levels become too low, if we inject too much insulin, this is a condition called hypoglycemia, hypo for too low, glycemia for sugar. Hypoglycemia is considered far worse than hyperglycemia. Severe instances can triple the 5-year mortality rate for a person with type 1 diabetes. It can cause someone to be less sensitive to whether or not they're becoming hypoglycemic in the future. And there's another good example. It can cause someone to lose consciousness, which could be devastating, for example, if you're driving. So I see there's a question in chat. What about the situations where there's an undesirable behavior that the user doesn't think of prior to implementing the algorithm? That is that second path that I said we won't discuss in this talk. Also very important, but it's important to also say, once we know what we want to prevent, how can we prevent that undesirable behavior? So just to make that clear, imagine that we had some method for saying, what if the user doesn't think about this undesirable behavior? We'd need some other system that can reason about and recognize we should still not do that. But once we have that undesirable behavior, then we need a system that can, with high probability, avoid that undesirable behavior. So we're tackling one side of this problem, not the side of behaviors we don't think about. Another question says, since many of the uses of AI and ML are being programming APIs, would one interface need to be through these programming APIs and the user defining the safety parameters be a software designer using the AI ML programming API? So the API, so for example, for the fairness case, the API would be something like this console. For something like reinforcement learning, the API could be something along the lines of what I'm about to describe, where a person labels images. But separately, someone else would have to find a way for their application to convert historical data into these image traces, which it's clear how to do that in diabetes case, but for other applications might take more work. But we're not tied down to one interface. I would love in the long term if this interface was a natural language conversation with the system. We're not, as I'll get to in a bit, we're not proposing an algorithm. We're proposing a new set of properties that we would want of an algorithm, and then we'll show that this is feasible by creating example algorithms that work in this setup. Okay, right, so back to the diabetes example. This low blood sugar is especially dangerous, and so we want to make sure that we don't inject so much insulin that we cause hypoglycemia. So how could a medical professional in this case say, this is what undesirable behavior means for my application? Well, what if they can look at these plots? Sorry, my slides are not transitioning. There we go. What if they can look at a plot of someone's blood sugar throughout the day, and hypoglycemia is when it goes below a threshold, in this case, the dotted red line, and label them as the undesirable outcome is present or the undesirable outcome is not present. This could be another interface. And in this interface, the safety guarantee that we would give is we will not increase the frequency of this undesirable outcome relative to whatever solution is currently being used. So in this case, that would mean we will not change the policy, the rule for how much insulin to inject, to one that increases the frequency of hypoglycemia. And the probability that we guarantee this with will be 1 minus delta. Okay, so those are just two examples of interfaces. So to delve into this a little more formally, we'll need to introduce some math. So let's start with some notation. Let's let D be all of the available training data, and this is going to be a random variable. Let's let theta be the set of all possible solutions that the algorithm can return. We can then think of a machine learning algorithm as being a function that maps data sets to solutions. And so A of D is the solution returned by the algorithm when it's run on data D. And that's a random variable because D is random. Then we'll assume that there exists a function G, which measures undesirable behavior. So that if G of theta is less than 0, so theta is the solution, the weights for my neural network, for example, that's returned by the ML algorithm. If G is less than or equal to 0, we say that theta is safe, or it doesn't produce the undesirable behavior. And if this value G is greater than 0, then we say that theta is not safe. It produces the undesirable behavior. Now, of course, we do not know G. The user doesn't know G, but the user will convey the G that they want to us via the interface, right? That expression that we typed in the console before was a definition of G, for example. Okay, so given this notation, what is a Seldonian algorithm? A Seldonian algorithm satisfies this equation. Remember, A of D is the solution that's returned by the algorithm. G of A of D is this measure of how unsafe or unfair that solution is. When that's less than or equal to 0, we say that the algorithm has returned a safe or a fair solution. And so we're saying the probability that the algorithm returns a safe or fair solution must be at least 1 minus delta. Some properties of this: the user is choosing the definition of G via the interface. The user gets to choose delta. And we do allow for multiple different constraints by specifying multiple G's and multiple deltas. For simplicity in the talk, I'll just limit myself to 1. And there's another condition. So giving an algorithm with these properties simply is not possible. I can give you a constraint, a definition of G that is impossible to satisfy. This comes up in fairness. There are conflicting fairness definitions, where I could say, I want this robot to follow the center of this lane and never deviate from the speed limit by more than 5 miles an hour. And in some places, you cannot go 5 miles under the speed limit without skidding off the road. So you can ask the impossible of the system, and it needs a way to say, I can't do what you asked for. Another case where this comes up is if you ask for a high confidence guarantee and you just don't give it enough data in order to actually give that guarantee. I say, guarantee that you're fair, and here's data from 2 people. That's not enough to do it. So the algorithm needs a way to say, I cannot accomplish what you asked. And this is a consequence of having this flexibility that the user can define safety or fairness for their application. So we have this additional solution, NSF, standing for no solution found, and we define no solution found G of NSF to be 0, meaning it is always safe to say, I can't do what you asked for. Now, you might note then, okay, well, we just defined a trivial problem. Just produce the algorithm that always says no solution found. And that's right, that is a safe or fair algorithm under this description. But the key is that this equation is the safety constraint. This is not the primary objective. This is just the safety constraint. We still want our algorithm to be good under some primary objective of accuracy or performance, and to often not return no solution found. And in our results, we'll look at how often does the algorithm have to say, I can't do it. Someone asks, what assumptions are being made about the data sets? So no assumptions at this point. Once we present an algorithm, we would need to introduce some assumptions that algorithm makes. But for now, we're actually just proposing a framework for algorithms. Think of it like we're proposing classification algorithms, right? You can create classification algorithms with different properties. Right now, we're just saying these are the general properties we want in what we'll call a Seldonian algorithm, which is a class of algorithms like classification. And then we'll give some very simple examples of what of some algorithms and perhaps the assumptions they need. Hopefully, I'll be able to get to that. Okay, so this leads right up to the next question. So I've just described this great framework. Great, what is the Seldonian algorithm? Let's present the algorithm. There is no such thing as the Seldonian algorithm, right? This is more of a what we want in an algorithm, not what is the one algorithm or how exactly are you doing this one thing. What we can do is provide some examples of Seldonian algorithms, but you shouldn't think of these as the Seldonian algorithm. They're just examples. And as we'll show later, I don't think they're particularly good. I think there's a lot of room for improvement, even though these very simple ones that we've already created are creating state-of-the-art results in terms of safety and fairness. So I still think there's tons of room for improvement. Don't think of these as like golden algorithms that I'm saying you should use this immediately today for everything, right? Okay, so here's one example of a Seldonian algorithm. Give me just a moment to look. There's a question in chat. This is related to posterior regularization. Perhaps I may come back to that later on. So how will this algorithm work? We're going to start by taking as input the desired constraint from G and delta and the data set D. Slides aren't advancing. There we go. We will partition our data into 2 sets, D1 and D2. We'll take that first data set and use it to run your favorite machine learning algorithm, and it will produce some solution, some weights for your neural net, some model. We'll call that model theta C. Theta C stands for candidate solution. It's a candidate that the algorithm is thinking about returning, but it's not yet ready to. Next, we'll take that candidate solution and run a safety test that checks, does this solution satisfy the safety or fairness constraint that the person put in through the interface? If it passes the safety test, we return the candidate solution. Otherwise, we return no solution found. So let's dig into these different components. And by the way, if you're thinking, this is exactly what I would do as a data scientist, that's exactly right. In a sense, we're automating the job of a smart data scientist who's partitioning their data, training a model, and then validating that it's meeting the safety and fairness conditions that they want. But as we'll see, this ends up being a bit more complicated than you might expect and harder for the data scientist than you might initially expect, particularly when the safety or fairness conditions conflict with the primary objective, in which case candidate selection needs to carefully balance the trade-off between the safety or fairness constraint and the primary objective. Okay, so let's give an example of how this safety test might work. The reinforcement learning case, I think, is more complicated and perhaps more interesting for this audience, but we just don't have time to go through in detail. For those familiar with it, we're going to basically use importance sampling with confidence intervals strapped on top to get high confidence off policy predictions of performance. But back to this example. So remember when we had this fairness example where we were predicting GPAs. How does the safety test work? Well, first, we take the expression the person typed in and we build a parse tree out of it. Next, for each variable, we either assume that it's a constant, like the number 1, or it's a term that we know how to get a confidence interval for. And so these could be most common parameters of a distribution. We can get confidence intervals from a data set. So in this case, it's the mean squared error, given that someone's male or female. And in this case, our system has several of these variables built in that you can automatically use. You can then add any additional variable to the system that you can get confidence intervals for. Okay, so we get confidence intervals for the mean squared error, given that someone's male, confidence interval for mean squared error, given that someone's female. And if you're curious, how do we do that? You use your held out data. You run your model on the held out data, and you compute the mean squared error on that held out data. That gives you a point estimate. From that, to get a confidence interval, you apply something like student t-test or Houghton's inequality. Okay. Once we have these confidence intervals, we can push this interval via interval propagation, it's called, up through the parse tree to see what is a confidence interval on the difference between these two, then the absolute value of these, take off the constant. And in the end, we get a confidence interval for G. And remember, if G is less than or equal to 0, we say the model is safe or fair. If it's greater than 0, it's not. So now we simply check, is this confidence interval, is the upper limit of it less than 0? If so, we return the candidate solution. We can say that one is safe with high probability. If it's not, then we do not return it. Okay, so that's the safety test. How does candidate selection work? As I mentioned, it could be your favorite off-the-shelf method, but this ends up being more complicated than you'd think. The challenge is the model that you think is best may not be one that will pass the safety test. So how do you balance the knowledge of, I want to maximize performance, but subject to, I want this to pass the safety test? So really what candidate selection should do is optimize your primary objective, but limit its search to the solutions that it predicts will pass the safety test. So we use D1 to predict the outcome of the safety test using D2. So what do I think the safety test will return when run on D2? And then we limit our search to only those solutions that we predict will pass the safety test. Okay, so does this work? And I see there's a question. How do you generate sufficient test cases to say with confidence that your test set is represented enough to create the confidence intervals? So for example, in the case of self-driving cars, the set of possible scenarios is astronomically large. Right, so what you need to ensure is that you're satisfying the assumptions of the confidence interval. You do not need to see every possible case, but so in that case, say we use Houghton's inequality. To apply Houghton's inequality, we need to have the bounds on the random variable that we're considering bounding. And even if there's some outcome we have not seen, say we've tested on 100 different types of roads, but there are actually billions of types of roads with different properties and parameters, that's okay. You don't need to see every sample for the confidence interval from Houghton's inequality to be valid, right? So what Houghton is essentially doing is saying, what is the chance that the samples that I haven't seen are actually likely, and I'm likely to encounter them, and thus they could cause the mean to shift. And it's already incorporating this and accounting for it. So I think this concern is handled automatically by the methods for constructing confidence intervals. But a key point is, notice, we are not saying the catastrophic event will never occur. We are giving a confidence interval that says with high confidence, the catastrophic event won't occur. Okay, so let's apply this to some example use cases. First, we gathered data from 43,000 students who applied to this university with 9 different entrance exam scores, and we tried to predict their GPA during the first 3 semesters. This was the University Federal Rio Grande do Sul in Brazil. We defined G to be the absolute value of the difference between the expected error, so y hat is the prediction, y is the true label, the true GPA, given that a person is male. So the expected over prediction given that you're male minus the expected over prediction given that you're female. Remember, we want this to be less than or equal to 0. So moving the epsilon over, we want this difference in how much we over predict to be less than epsilon. We use 3 standard methods, linear regression, and neural network, in a random forest. And what we're seeing here is the average prediction error for men in black and women in white. And this is GPA points. So these methods on average overpredict for men by 0.15 GPA points and underpredict for women by 0.15 GPA points for a total average difference in overprediction of 0.3 GPA points, which is a huge difference in GPA. our definition of G says we want these bars to be within the dotted red lines. We applied our algorithms and they succeeded at doing this. And this example is great because it says, look, this can kind of work. It's flashy, but it doesn't really tell us something about how well the algorithm is working. So what we really want are the following plots. First, we want to plot, and don't worry about what we're actually showing with the curves. I'm introducing the plots, and then we'll show some examples of these plots. So we want on the horizontal axis the amount of data that we have, and on the vertical axis, we want how often did we have to say no solution found? How often could we not handle the task? And what we'd like to see is green will correspond to our methods. We want to see our method going up towards 100%, saying with enough data, we're always returning solutions. Then we might ask, okay, so we're returning solutions, but how good are they? So on this axis, we again have how much data we have on the horizontal axis, and on the vertical axis, we have the accuracy of our model. So how good were the solutions we returned? And we shouldn't expect to necessarily perfectly match an unsafe or unfair method because it has no safety constraints it needs to deal with. But we'd like to see that our drop in accuracy is not too large and that ideally with enough data, we can still get very good accuracy. And in this case, the green is us, the lower ones are some fairness aware algorithms. The top, I believe, are fairness unaware algorithms. And so those can achieve the best accuracy. And we're also with enough data achieving good accuracy. And the final thing is, how often did we mess up? How often did we actually return a solution that violates the safety constraint, that with high probability, that with probability more than delta, returned a model that was unsafe according to the user's definition? And in these plots, so this is the probability that G of A of D is greater than 0. In these plots, the dotted black line is delta. That's the probability we want to stay underneath. And we want our green curve to always be underneath that dotted black line. So for the GPA prediction example, there are many different definitions of fairness. And so we took 5 of the most common: disparate impact, demographic parity, and equal opportunity. And I'm not going to run through these in detail just for the sake of time. The key is on the left. Our green curve approaches the accuracy of all the other methods. We're not losing too much accuracy. In the middle, our solution rates are going up to 100%. And on the right, our method is staying below that dotted black line. The green is beneath, whereas the competing methods, in this case, the fairness aware ones or fair learn and fairness constraints, do not stay below that dotted black line in all cases. We also did this with equalized odds and predictive equality definitions of fairness. We're submitting to ICML shortly, one that deals with delayed impact notions of fairness. We can also do this in the reinforcement learning setting. This was for type 1 diabetes treatment, where the horizontal axis here is the amount of data that we have in days from this person. And here we're showing the probability of solution and the probability that we returned a solution that increased the frequency of hypoglycemia. Green were variants of our methods and black was standard RL approach. And you can see we are returning solutions with reasonable amounts of data. 3 to 6 months is what you'd hope for, and we're well beneath that. And our method never returned solutions that increase the frequency of hypoglycemia. I should say, what were we using for this? There's a simulator called T1DMS. At the time that we were doing this experiment, if you wanted to do studies on humans with these insulin pumps, the insulin injections, you had to do studies on rats first for the FDA to approve this. Or you could use this one simulator. So it's not a perfect simulator, but it is a very good simulator that we purchased. I'll skip over this result, but just another example of a control task where we were enforcing fairness. Okay, so in the context of building on top of methods, I think of machine learning, deep learning, reinforcement learning as these very built up areas where we already have a very solid foundation and we're kind of tacking on these little bits on top. This space of creating algorithms that have high confidence safety or fairness guarantees is relatively underexplored, and there's tons of work left to be done. But I will talk about some of the advancements we've done since that initial paper to extend this to other settings. So first, in the science paper, we looked at fairness for supervised learning and safety for reinforcement learning. In this paper, we considered fairness for reinforcement learning, or the special case of contextual bandits. We applied this to a tutoring system on Mechanical Turk, showing that we could, that standard systems could change online tutorials in ways that are better for a majority group, but worse for a minority group in the classroom. And if that increases the overall scores on exams at the end, a standard approach would do this. And so we enforced fairness constraints in these online tutoring systems. We also did it for a loan approval example and for predicting criminal recidivism. Okay, next up, and I'll break these other papers down by which piece of this diagram they're improving. Looking at improving the safety test, one of my students, Yash Chandak, showed how in the reinforcement learning setting, we can give safety guarantees, not just with respect to expected performance of the system, but with respect to the variance of the performance of the system. And if anyone's more curious about that and familiar with importance sampling, I can delve into why that's a really interesting task. And at, which was this? At the just past NeurIPS, we presented universal off-policy evaluation, which takes us one step further. And in the reinforcement learning setting, lets us give high confidence bounds on any parameter of the distribution of performance. So not just expected value, not just variance, but also things like conditional value at risk, quantiles, value at risk. Any parameter that you might want of the return distribution, we can now bound with high confidence and use as a safety definition. We also extended this to the case where the world is non-stationary in this paper towards safe policy improvement for non-stationary MDPs. So the key thing in this plot is the black line is the performance of some current policy that we're using. In every normal RL paper, this would be a flat line. The performance of a policy, of a fixed policy, does not change over time. But in the real world, that's not true. The real world is changing. The environment constantly shifts. So the performance of a policy in this case is this curved line that goes up and down. And the red line is the performance of a standard Seldonian algorithm that is not aware of this non-stationarity. And you'll see it dips below the black line at some point. The solid red line dips below, whereas the solid blue line, which is the performance of the new algorithm, always either says no solution found, deferring back to the black line, the current policy, or when it does change the policy, it's only being an improvement. It's going up relative to the current policy. We also have some work for safety tests outside of RL that allow us to give bounds on risk parameters, specifically conditional value at risk. This is the state-of-the-art confidence interval for conditional value at risk. And we have a new state-of-the-art confidence interval for the mean, which sounds absurd that this is such a heavily studied topic. How is there still room for improvement? It turns out there's massive room for improvement. This paper beats Huffington's inequality and Anderson's inequality, two of the common confidence intervals for the mean. But there's another one, which I'm happy to talk about later, which we call Gaffkey's inequality, which remains an open problem to prove that it's a valid confidence interval. And it absolutely dominates all of these. So there's still surprisingly a lot of room for improvement and research in creating new bounds on the mean. Okay, we can also ask questions about the data set. So this student, James Kostas, studied the question of what if the data set isn't historical data from running a current policy, but we have some sort of distribution over simulators and we want to generalize over the distribution of simulators with high confidence, with also similar results. This student, Pinaro Zizek, studied the question of how robust or safe or secure are our algorithms. What happens when we're learning from handwritten doctor's notes and there's an error? What happens when an adversary can corrupt some of our training data? The Seldonian algorithms that we created, especially in the reinforcement learning case, if you can corrupt one data point, you can completely violate all of our safety guarantees. And so Pinar showed that this was the case and showed how we can make our algorithms robust to an adversary who can corrupt alpha% of our data. And we were motivated by this application to sepsis, where it was handwritten doctor's notes. Stephen Jagir looked at the question. So someone asked, what are the assumptions on the data set? So our initial algorithm assumed in the supervised learning case that each data point is drawn IID from some distribution, and that distribution will be the same at train and test time. Steve looked at the case at what happens when the distribution of data that I have to train on differs from the distribution of data that I'll see in the future. And he studied this in two different settings. One was when this is fairness, and it's just demographics that are changing. So if I train a model in LA, because of the differences in demographics, even if it's fair there, when I deploy it in New York, it may not be fair. So using census data regarding differences in demographics, can we fix some of that shift? And then he has a separate piece of work that looks at what about general distributional or covariate shift. Right, I'll skip over this one for now. That paper that does fairness in the RL setting has a neat result showing that if a fair solution exists and the limit is we get infinite data, we will be able to find and return it. So we have some papers kind of scattered around this landscape of Seldonian algorithms. There's so much more room for improvement. So I want to briefly talk about open problems and things that are still left to be done here. So when our algorithm says, I can't do it, why can't it do it? Is there not enough data, or are you asking the impossible? If you're asking the impossible, is it due to multiple conflicting safety requirements? And if so, can we tell you which ones are conflicting? Can this be combined with explainable AI techniques? I love that we can give high confidence guarantees, but it's not enough to go to a doctor and say, this will be better with high confidence, because they may say, prove it, explain beyond just math. Why will the treatment that it recommends actually be better? It would be great if we could explain why that model is actually safer there. So far, I've talked about the batch setting where we get some data, we train the model, and we give a guarantee. Can we do this in the online setting? And I suspect the key to doing this will be the confidence sequences coming out of Aditya Ramdas's work at CMU. Within the safety test, can we get confidence intervals for other parameters, like our work on conditional value at risk? Can we get tighter confidence intervals? We have some ideas that this way that we're propagating confidence intervals through the tree could be drastically improved and tightened. So things like, when I want this to hold with probability 1 minus delta, I need all of my confidence intervals on the leaf nodes to jointly hold with probability 1 minus delta, which means if you're using something like t-test or Hufting, you plug in delta divided by the number of leaf nodes. You don't need to evenly distribute your probability of failure across the leaf nodes. Can we optimize how we let those different leaf nodes fail, their probabilities of failure? Can we optimize that to optimize the resulting confidence interval in the end? And there's some other really interesting tricks, like the order that you bound the leaf nodes can change the tightness of your bound. Because, for example, if it's A times B, if I bound A and I conclude that A is strictly positive, and I want an upper bound on A times B, by knowing now that A is positive, I only need to upper bound B. I don't need a two-sided bound on B. So the order that you choose to bound these variables matters, and that's not something we considered. Can we stop doing frequentist confidence intervals and do Bayesian credible intervals? Can we improve our off-policy evaluation methods in the RL case? And there's a large body of work. It's kind of the main area I've worked in prior to this is off-policy evaluation for RL, which is these safety tests for RL. And there are tons of problems to address in that space and get further improvements, all of which will make these algorithms better. In candidate solution, I'll skip over this. In our candidate solution methods, you can think of them as saying this argmax at the top says, maximize the performance of our model, maximize accuracy or expected return in the RL case. And then the subject to down beneath says, subject to, we predict the safety test will pass. And this prediction here is for the safety test based on students' t-test. Actually, it's exactly the safety test if you remove the big red 2. But it doesn't work without the 2. And what's happening is in candidate selection, we're overfitting and finding a model that we predict will pass the safety test, but really it won't. We've just overfit during candidate selection. And by inflating the confidence interval with this 2 in candidate selection, we avoid that overfitting. This is a completely unprincipled hack. I put that 2 in there to make it work, and it works reasonably well, but a principled solution could make this work even better, giving us solutions with even less data. And so I just want to reiterate, I think of these existing algorithms like this bicycle. They're proofs of concept showing that it can work, but they're a duct taped together solution from existing components. That's the first attempt, and there's tons of room for improvement. Oh, right, and that 2 is only really necessary when the safety constraint is conflicting with your primary objective. Also, is there a benefit to not just returning one candidate solution, but to returning many? Actually, in the diabetes route, we did the safety test first. We enumerated a large set of possible solutions, checked all of them for safety, and then picked the one that we think is best, which is kind of like this returning multiple candidate solutions. And also there's that argmax in candidate selection and an issue of how do we do that for larger problems. Other issues are, and I'll speed up because I know I'm running low on time, how much data do you put into each of these 2 sets? How do you split train test? They're rules of thumb, but they're not optimal. Really what this is, I think, is it's an optimal stopping problem. You should put data into D2, and then the candidate selection mechanism should pull data out of D2 and should keep pulling as long as it's increasing the chance that the solution it returns will pass the safety test by finding better solutions and getting better bounds. And at some point it should say, I need to stop pulling data, because if I keep pulling more data, my prediction of the safety test, the confidence intervals in that safety test will grow wider because I have less data at testing time. And so I need to stop pulling data out of D2 into D1. Also, can we use notions of stratified sampling? Can we make our algorithms more robust to missing data, more robust to distributional shift? Can we soften the independent assumptions? Someone asked, what are the assumptions? The framework makes no assumptions, right? The question then is, can we make methods that give high confidence safety guarantees subject to different loosened assumptions? Can we make better interfaces? Ours are great starts, but I'd love natural language. Can we use learning from demonstration for robotics tasks? Could they be described using some different notions instead of rewards, but first order logic? Can this whole setup be changed? This is the first way that we came up with for creating these algorithms. Can we completely change how this algorithm works? And can we apply this to new problem settings? I haven't done this yet for natural language or computer vision problems, and we have not touched at all unsupervised learning. So what would this look like for unsupervised learning? So the main takeaways are, I hope you take these away from the talk, are creating these safe and easy to control ML algorithms is an important problem. One framework for doing this is Seldonian algorithms, which just means algorithms that have an interface that let the user define safety or fairness, and that then give high confidence guarantees on top. And that I hope you also take away that we can create these algorithms. This is not asking the impossible. We've given some examples of safety for diabetes treatment, fairness for these many different applications, to show that we can create algorithms with these properties. Our existing algorithms are just prototypes, but even as prototypes, they're quite effective. And hopefully maybe some of you would be inspired to say, I can do better than this. I know how to improve that component. And perhaps you can then create an even better Seldonian algorithm. If you want to make some of these or toy around with them, at this website, aisafety.cs.umass.edu, the tutorial section runs you through creating a very basic one. This is, I believe it's doing basic Seldonian algorithms for regression with a really simple interface that's not easy to use, but it's a starting point. And then it points you to how you might create other interfaces. And also, we just received funding to hire a software engineer to create a Seldonian ML library with different modules plugged in for reinforcement learning and fair ML. So hopefully about a year from now, if you click that code link, you'll be sent to a library that you can just directly apply to applications. And I see there's one question I missed. I'm wondering if you can provide more details on the candidate selection stage. How do you change the selection of theta C when your outcome doesn't meet your constraints? Is it ad hoc or is there a systematic way? So actually the equation that we use in pretty much all of our examples is that one with the big red 2. Let me find it. Right. So it's this one with the big red 2. And I guess, how do I describe this? So if you think about the classification setting, F hat is your classification loss. You can pick your favorite loss function. And a normal ML algorithm is just doing that top bit. Find argmax over your solutions. The one in this case would be min for your classification loss. So what are we doing differently within candidate selection? We now want to say subject to the safety test will pass. So that subject to, that expression is exactly the safety test. If you're trying to parse it, the green term is the sample mean for the G hats are unbiased estimates of G. And we're trying to say, ensure that with high probability, G is less than or equal to 0. So we're taking the sample mean of these unbiased estimators, G hat, and then t-test tells us what amount we need to add to that for the confidence interval. So that's the green bit. Some interesting parts here are D1 is the data used for candidate selection. D2 is the data used in the safety test. N1 is the size of D1, N2 is the size of D2. You'll notice there's a weird interplay of N1 versus N2 here. Actually, one of them is unlabeled. That one should be N1. And that is because we're trying to predict the outcome of the safety test from the training data. And then the 2 is simply inflating this. So that is exactly how candidate selection works. On the question of, do we change the chosen theta C? We don't. So this would cause a problem. So imagine that we chose one candidate solution, we ran that safety test, and the safety test said, I cannot give you the guarantee you want. If we then said, okay, let's try a different solution, and we reran that safety test, we're effectively running 2 hypothesis tests. And we're saying, let's just keep checking hypotheses until one comes back as, yeah, it's safe, right? So we're all familiar with multiple comparisons. This is the multiple comparisons problem. We would end up returning a solution that's unsafe with probability more than delta. And we could potentially fix this by using something like the union bound or Boole's inequality. to test theta C, not with a failure rate of delta, but a failure rate of delta over 2. Now, if it fails, we can run back and try one other theta C. And if you're interested in, well, okay, what if I want to test more than 2 solutions? I think the confidence sequence work from Aditya Ramdas might be viable for letting us test more of these without hitting multiple comparisons. Okay, there's another question. Also, how do you solve each constraint optimization problem when it's non-convex? SGD is for unconstrained problems. Great question. So let me go to that future work on, oh, actually, right. So the bottom one on this, which I kind of grazed over, how do we approximate the argmax for large problems? So the way that we've been doing this now, when we do criminal recidivism, predicting loans, GPA, or diabetes, these are all relatively small problems. The dimension of theta is less than 100, right? So it's not a high dimensional problem. But if I'm training a neural network, and this is why we haven't yet done it for NLP or vision, you probably have millions of weights you're training. So how did we solve this argmax? The way we solved it is with the algorithm CMA-ES. If you're not familiar with it, the Wikipedia page is wonderful, but it's essentially a black box evolutionary algorithm that does not use gradient information. So it's not very efficient. That worked for our relatively small problems, but it does not scale to training something like a neural network. If you want to train a neural network, which one of my students, Chris Noda, did this once for a neural net, the route toward this is probably to roll this constraint into your objective using Lagrange multipliers or the KKT conditions. And now you have a global smooth optimization problem, but it's not, as you said, convex. So you'd want to probably do something like random restarts. One really nice perk of this is, let's say that the optimization fails and doesn't return a good solution. That does not make our algorithm unsafe. It will just make us return no solution found more often. More often we'll have to say, I wasn't able to do it. It doesn't make the algorithm unsafe if that optimizer fails.
I see that Tony has a question.
Yeah, first of all, Phil, thanks for an excellent talk. I really enjoyed it. My question is whether this approach can signal to the user that there's a variable or a feature that's not included in the model that should be. In other words, something is wacky, and maybe it's because the user didn't include something like the weather in the model or something. So you know, there's something that's really off that could be discernible in this approach.
That is something I should add to this list of future work. We do not have a way of doing that right now. But if there was a way or an approach for doing this, I think that would fit in beautifully as a piece of future work for creating a Seldonian algorithm that can tell you, I think there's a feature missing for me to be able to solve this problem well.
Thank you.
So I think we're at the to the top of the hour. Phil, amazing discussion. I had a number of questions along the way, and you answered them along the way. So I ended up with no questions, and just a tremendous amount of depth and breadth in this subject area. I think it's just going to go a long way in ensuring safety and fairness in algorithms. So really appreciate your presentation. I think everybody else did as well. Thank you very much.
Thanks everyone for taking the time to come to the talk.
Take care.
Bye everyone.
And Dr. Thomas, bye everyone.